what we've done.
And the funny thing is, if you add all the coefficients together, you get 0.
Well, what matters is if you square the coefficients, what should they add up to?
1.
They should add up to 1.
It's probability.
That's the probability.
And that's the probability. Yeah, so what have we done? Here, what is this over here? This is our coupled state. And it's built in terms of the uncoupled basis. Okay, so then the next question they ask is, for example, looking at this, what is the probability that I would measure for particle 2 a spin projection of 1?
1/6.
1/6.
1/6. All right? It would be a half. Okay, kind of get it. It is confusing and it makes you go crazy until you put in the groundwork, all right?
If it's the z component of h bar, would it be h bar times?
It would be h bar. You need the h bar. These go without the, I'm saying it all without the h bar.
Yes, this is assuming h bar is a common factor.
Right, because the chunks of any momentum are in h bar.
I have a question not related
Yeah,
to this, but
H bar.
is it hard, really hard to calculate these, or is it just time consuming to do it by hand?
So I have to remember back to 1991 when I wrote code to do this, and I can't say that I recall how to do this by hand, unfortunately.
Look at the coefficients.
Yeah.
Yeah.
If they're named after someone, then they're hard.
Well, I'm just
Yeah.
wondering if they're hard, or if they just take a long time to do. Maybe
Oh,
that's
sure.
not that hard.
So I wrote, so one of my thesis, part of my thesis is I needed these. So I wrote a code in BASIC that made the kets with like a line up and then a greater than symbol.
Yeah.
So I was making symbolic algebra codes, you know. And then I,
That's only 10 years ago.
You have to do that.
oh, wait a minute.
91,
Yeah,
that's
no.
91. 20 years ago.
20 years.
20 years ago, yeah.
You have to do that with wet stuff too.
Yeah, I finished my PhD in 93. And so in the back of my thesis, it shows the code. So Dale, I can't.
I was just kidding.
Answer. It has to do with these, it's all symmetry, and it's all the stuff by Eugene Wigner. And they're called Wigner 3J symbols and Wigner 6J symbols and things like that. And I think that what happens is when you get down to that level, there's just a fundamental formula, you know, that
They do it in Sakurai. He kind of touches on it in Townsend, doesn't he?
don't remember, okay? But those are Wigner 3J and 6J symbols, to the best of my, I haven't done that in a while. Okay, so anyway, that answers that question, and, you know, that's A. And then B, 436B is another good one.
While you were erasing, is this the same Gordon as the Klein-Gordon equation?
Good question, I don't know the answer to that.
That's what I say, that was a while back.
Yeah.
Like, time-wise, because this quarks must have taken place later on in the 20th century.
But he wasn't talking about quarks, he was talking about having angular momentum.
No, I'm saying with the time scale,
Yeah. I'd like to know that answer, I don't know.
yeah, it must have been,
Klein-Gordon is,
Ask Wikipedia.
yeah, yeah. So let's
must
look
have
at
been old is all I'm saying.
the next one is, yeah. I mean, quantum mechanics is 1900 to 1930s.
Right, but I'm saying this must have taken place a lot longer after.
Well, I mean, Dirac was alive in the 70s. So.
Dirac was alive in Florida
Yeah,
State.
Florida
Florida State.
Yeah, yeah.
Okay, so the next one is, I have a hydrogen atom with a psi given by 510. Okay, so remember, 5, these are the 3 quantum numbers of a spherical problem, so 3 degrees of freedom. You need 3 quantum numbers. This is N, L, and ML. But the big scoop is that L equals 1, right? This is L.
And m equals 0.
All right, ML equals 0. And it's I think it's a 5s electron. So this is, I think this is rubidium. So 1s, 1. It's a
Is that-
flat shell.
Is that in the table that you give back?
It should be, I think it's rubidium.
It just says it's,
Oh, you know, what it does is it uses, it's just hydrogen, so it's an excited hydrogen. But this could also be like
Yeah, it
rubidium.
could be anything with a closed shell,
Doesn't
just
have
as
to-
hydrogen like.
Yeah, so don't forget, anything with a closed shell, what is the total angular momentum?
0.
What is the total spin?
0.
0. So the angular momentum of atoms that are even big are just reflected in the outer shells that aren't filled. Right? Okay? Okay, so if you could measure the total angular momentum squared of the electron alone, not including the proton, what might you get and what is the probability of each? Okay, so here's the first case. We have an L equals 1 and we have an S equals a half. So again, if this is an atom, you know, here's an atom, and I draw my cloud around it, what has to be true about the total angular momentum?
has to equal on that.
3 be conservative.
Okay, so again,
Well,
sum of
conserve.
torques equals dl dt. So what has to be true about a total angular momentum?
Conserve.
It equals conserve. So L total, that's all we can say. So all we can say by physics is that the total angular momentum is conserved. But because we know it's angular momentum, it's like a vector, we know what the possibilities could be. So here's what I generally do. If I'm coupling together an L and an S, I create a new quantum number J. All right, and J simply represents the coupling of a spin angular momentum in an orbital angular momentum. So in this case, I would say L plus S is greater than or equal to J, greater than or equal to L minus S absolute value. So it's not a big deal though, because they're angular momenta, right? So it really doesn't matter. So here you have a 1 plus a half is greater than or equal to J, which is greater than or equal to 1 minus a half. And so in other words, a J can equal 3 halves, or the J can equal 1 half. Yeah? Okay, so what are the possible coupled states that you could have of this atom?
Well, this is spin down, so it's a negative, MS is negative 1/2.
Okay, so if you have a total J of 3 halves,
Yeah,
right,
3 halves.
then the projections, so this is kind of
4
like,
projections.
yeah, so 3 halves, minus 3 halves, minus a half, 1 half, minus 3 halves.
You put minuses on both your heads.
Oh, sorry, yeah.
All right.
And then what else could I have for this atom?
You have 1/2, which just has negative 1/2 and 1/2.
Right. All right, and then again, this is super sloppy. You know, you've got to be careful. I'm talking about distinct states here. Okay? If I have an atom, say I approach an atom, right, and it's just sitting there, and it's not in any particular, well, if it's not in a magnetic field, I haven't defined any type of projection, any type of direction, all right, then it can be in any one of these states. All I know is that J is 3 halves or J is 1 half. But as soon as I define a direction, and usually do that with a magnetic field, then how many states did this atom take as soon as I put it in a magnetic field?
You know, take 1.
It only takes 1 out of how many?
4.
Well, 4,
5,
6. So in other words, this atom can be in any one of 6 states once I slap on a magnetic field. All right, and that's how I calculated the probability. They said, what is the probability of each? And what I did is I calculated the total number of states that I could make. Yes. Yeah, so it asks if you can measure the total angular momentum squared, all right, of the electron alone, what might the values get and what would be the probability of each? So the total, what would the total angular momentum squared would you get? Total angular momentum for the system. What are the possibilities of total angular momentum?
3 halves or a half.
3 half squared or a half squared. All right. How many so what would the probabilities be then?
9/4 and 1/4.
No. So if I'm going to measure this number, how many states are here?
1.
4. Four possibilities, and how many here?
6.
2. So 6 altogether. So what chance do I have of measuring of 3 halves?
2/3.
2/3. 4/6, and the other?
A third.
A third. Okay. Everybody got that? A little messy, guys. Super messy. All right. Let me do another example. All right. Say, so this is a complete side note. Say I have helium. So there's a proton, and then there's a 1s electron, and then there's a 2p electron. Right, a 1s electron and a 2p. Everybody kind of got it?
Yes.
So ignoring the nucleus and the spin of the nucleus, all right, what are the possible states that I can have in this system? And it's a little bit trickier. All right, because now I've got 2 angular momenta and I've got 2 spins. All right, so there's different type of what are called coupling schemes. All right, and one of the schemes is called LS coupling, and the other is called JJ coupling. All right, and so in LS coupling, what you do is you couple together the total L's together, and then the total S's together.
With JJ, you do LS for each one.
And then with JJ, you couple the L's and S's of each together, and then couple it all together.
So the LS of the 1S, LS of the 2P.
Okay, let me tell you when you use these. It's related to perturbation theory, all right? But generally speaking, you use LS coupling when you have very light atoms, hydrogen, helium, lithium, beryllium, carbon. And then you use JJ coupling when you get way, way up to the very heavy atoms. So almost always I use LS coupling. All right, so here's how I would do it, okay? So here we go. So we have, I would do it like this. L1 equals 0, L2 equals 1, S1 equals a half, S2 equals a half. So I'm going to do LS coupling. I'm going to couple the L's together, then I'm going to couple the S's together. So here's how I would write it. I would go down here. I would go L1 plus L2 is greater than or equal to L total, which is greater than or equal to L1 minus L2 absolute value. And over here, I would couple the spins. S1 plus L2, S2 is greater than or equal to S total, which is greater than or equal to S1 minus S2. So what are the values of L that I can have?
1.
So L total can equal
1.
and
1. 1 or negative 1.
0.
0 plus 1.
oh, right, that's right. L total is just 1. Sorry, I was thinking of 0. L total equals 1. All right, and what about S?
1 and 0.
Okay, S total can equal 1 and 0. Okay, so then what you do is you take these two possibilities and you combine them together. And what you do is you make a giant state right here, which is called L, and then S. And so here, the only values of L you can have are 1, right? Right? What are the values of S that you can have?
1 or 0.
A 1, and then you can have a 1 and a 0. okay? But you don't usually put in the numbers, you usually designate it differently. If you have an angular momentum of 1, what is that? What letter do you have?
H bar.
What letter, like S, P, D, F?
S.
S is 0,
No, P.
so P. So these are both P's. So this is called like spectroscopic notation. Now, if you have a spin of a half, a spin of 1, total spin of 1, how many projections of spin can you have?
3.
3. 1, 0, minus 1. So this is called a triplet P. And if you have a spin of 0, how many can you have?
1.
1. So that's a singlet P.
So basically technical orbital, SP.
It's just describing the state of these two. It's describing the angular momentum state of the system that you could have. All right, and it goes further. What you usually do is you put J down here. Okay, so check this out. If you have a triplet P, what are the possible values of J you can have?
1, 0,
So if P is 1 and S is 1, if L is 1 and S is 1, then J could be 1 plus 1
2,
all the way down to
0,
1 minus 1.
3, 0.
So J could be, 2, 1, 0. And then what would this J be?
0.
That's one.
It's 1. Just 1. So that's why it's a single.
And for the S, you can just write,
What's that?
for the S, you just write 2, 1 times the spin plus 1.
Yeah, so in general, the state that you write up here, this comes from 2s plus 1. So for example, if it's a single, it's 2 plus 1 is a triplet. If the total spin is 0, it's 0 plus 1 in the singlet. So this is where that number comes from. Okay, so that's those homeworks. And I gave you some other Clebsch-Gordan coefficients problem, but I think because I did that other problem in detail, I don't need to go over it anymore. All right? The other Clebsch-Gordan problems, everybody okay with that? Practice those. And then I gave a funky one that you had to look on the web for.
L4, L.
Yeah. Okay, so then real quick, problem number 4.45. All right, that had to do with looking at an s orbital. All right, and it asked what is the probability of having the s orbital be in the nucleus. And so the first thing you had to do for this is look up what a radial wave function looks like for an s orbital. All right, and if you look that up, it should be non-zero at 0. Well, so remember, you're going to get the radial wave function. So this is what's a little bit tricky. You'll get R of R equals U of R over R. Remember, we had to make that substitution? Okay? But in any case, this is given. This is in a table. All right, but does R alone, is that probability? So in other words, if I gave you that psi equals R of R, y to the L, ML of theta and phi, is that probability?
No.
No.
Yeah, square.
Okay, if I square it, psi star psi, I get R squared, y to the L, ML, squared. Is that probability?
It equals 1.
This is important, guys. Is that probability right there?
You have to take the integral.
What's that? I need to take an integral. All right, and then is this an integral right here, or do I need something else?
You have dr,
I need to have this space, the volume. So psi star psi is a probability per unit volume.
So you need to have whatever the volume.
Okay, so this would be like an r squared sine theta, d theta, d phi. Right?
Yeah.
Okay, so let me ask you again. If I find r of r, and I want to plot probability as a function of r, what do I have to plot?
Psi star psi d r cubed.
Okay, well, not dr cubed. Why would it be dr cubed? Oh, volume, d cubed r.
Alright.
Yeah, okay. Yes, but now we're just pulling out the one dimension. We're not looking at the theta and phi part. They're linearly independent.
You're taking the third derivative.
So what space, so I'm looking at, I agree with you. I'm going to plot r star r. And that's going to be probability per unit,
Volume.
Radius.
okay,
Just-
radius squared. Because think about it. This part of the three-dimensional
All right,
volume
you just make the.
doesn't carry any area, right? It just carries the angle part. This part right there. So what do I need here?
D cubed.
You give it.
R squared. So in other words, the integral of this thing equals 1. So dp, d probability, equals r star r, r squared. Whereas, where this is a probability per unit area. Everybody see that? Okay, so I asked you to plot this, right? And so to plot it, you have to get the radial function for an s orbital, square it, and then multiply it times r squared, and then plot this thing as a function of r. All right? And what you'll find is that at theta, at r equals 0, is the probability equal to 0? And the answer is no. Everything else, every other orbital probability is going to be equal to 0, but not for the s orbital. This is why the work I was doing at Yale, we were interested in s orbitals, because we were looking at nuclear physics inside of the nucleus with the quarks. So what's the only electron we can probe that's going to get a decent interaction with the nucleus?
Yes, orbital.
S orbitals. Those are fun to play with, because they spend some time inside the nucleus. All right, and so if you go through, follow the solutions on this, but once you get the plot, but make sure you get the plot. You have to have the plot, otherwise it's meaningless, all right?
When you say they spend some time inside of the nucleus, how does that even, like, physically happen? I know it happens mathematically, but how does it happen physically?
So you don't think of a physical electron.
It's
Yeah,
a wave.
it's a probability, so the wave function is in the nucleus.
But if a part of the wave function would be in the nucleus,
Yes, so
And-
therefore that wave function overlaps with the things inside the nucleus.
but if you have a negative and a positive, wouldn't that like stick?
You're thinking of particles. These are fields. Everything are fields, and the fields overlap.
Okay,
So your classical view is 100% wrong.
got it.
Okay, good. All right. And then part of that problem that was very nice was figuring out the probability. And the probability was incredibly small, but it's not 0. Okay? All right, so we got a really kind of crank now. All right, I
Small
spent
one.
too much time on that. So let's look at identical particles, all right? This is chapter 5, and let's go.
So while you were erasing the board, Paul Gordon came up with the Kalbeck-Gordon coefficients, and it was Walter Gordon who worked with Klein and Klein-Gordon.
Different coordinates?
Different Gordons, although interestingly, Paul Gordon, who came up with the coefficients,
Yeah.
actually got Klein-Gordon his first appointment as a mathematician at a university.
We just found this out?
Yeah. And, but interestingly, those coefficients were done in the 1860s. Like, well before quantum mechanics.
It's group theory.
Yeah,
Yeah.
it's kind of crazy.
Yeah.
And Gordon actually did work with Klein-Gordon, but found him to be an irritating person to work with.
No, interesting.
Yeah,
So chapter 5. Thank you, Mike, for that. That was cool.
there you go.
How do they relate to the Gordon's fishing?
Huh?
How do they relate to the Gordon's fishing?
No, I do like all that information. I think it's fantastic, tying the story together. Okay, so what we're going to do now is we're going to solve Schrodinger's equation for two particles, and the problem you want to keep in mind is, you know, for example, the hydrogen atom. Okay, so we want to look at, so up to now, have we done two particles? Hydrogen, in two particles, anything?
No, we've all done one part.
In one particle, infinite well, and then scattering states, and then three-dimensional, and then 3D box. We've never done two particles. All right? So here's what we're going to do. Let's take, for example, our proton and our electron. All right? And I asked you for problem 5.1 to draw a picture. So here's the picture that I'm going to draw. All right? And I'm going to call this R1. And I'm going to call this R2. All right? And here's some arbitrary reference right here. Okay, so this, if I go R1, so I'll sketch it in, and so this is where I find physics majors screw up all the time on vector addition. All right, but if I go R1 and then to its tip, I add the tail R2, but I go minus, so it'll go like this. This is minus R2. Everybody see this? This is R1, then this is minus R2. Then the resultant vector goes from here to here. So this is R1 minus R2. All right? And look, a vector is a vector this way of length of my arm is still a vector of that length of my arm that way. So that's this vector right here. This is vector R1R equals R1 minus R2. All right, it points from 1 to 2. All right, so that just gets some stuff in here. Let's do quantum mechanics, all right? So what are we where do we start? Do quantum mechanics, where do you start? Start with Schrodinger's equation, all right? So let's go h times psi total equals IH partial psi with respect to t. I'm not going to put the total in there, it's understood. All right, sure. What are we going to do next?
Do that time.
Okay, let's get rid of the time. Yeah, separation of variables, get rid of the time. And so what is my G of t going to be?
Each part.
Yeah.
Okay.
One line.
And then what am I left with?
Stationary.
Okay, so I'm going to get all stationary states, but now I'm left with Schrodinger's time-independent equation. Now, what variables is it going to be a function of, though? Well, let's think about it. Ultimately, I've got to write kinetic energy, right? And so what's the kinetic energy going to be a function of for two particles? Don't I have to know the kinetic energy of the first particle and the kinetic energy of the second particle? So I got to know the x, y, and z of particle 1 and the x, y, and z of particle 2. All right? So this is going to be a function of, I'll write it, this is again shorthand notation, R1 and R2. Right? 3 variables, 3 variables. So how many variables is this a function of?
6.
6. I have a 6-variable differential equation right now. All right? And that's going to equal what? Let's anticipate n for now, and that's going to equal En times psi n. Everybody agree? Yep. Next step is to actually write down the Hamiltonian explicitly. So let's write it down. So there's going to be an Ek plus an Ep operators. What's the kinetic energy going to be? I have 2 particles.
2 minus h power squared over 2m double each one.
Okay, don't forget the 2 different masses though, okay? So it's going to be minus h bar squared over 2 mass of the proton times del squared, and the proton I said was particle 2, del 2,